Now, let's cover the climate classification system I use for all my climate maps nowadays. It is made by Nikolai from World Building Pasta, a blog which I highly recommend you read, link in the description, and is officially called either the Hersfeldt or Pasta Bioclimate system. But first, there is some follow up. I did a rerun of Exoplasm because I screwed up the timekeeping the last time, and not that much changed with the exception that the northern islands become oceanic boreal instead of tropical twilight. The updated map is shown on screen. Oh, and if you're interested in the raw climate output, say it in the comments. I haven't gotten rid of the final data. Anyway, now onto the actual system. In the last video on the Geb catalog, the home world, I did cover the top level categories in the system, but not much more than that. This video, obviously, will dig into the system in a specific glory. Now, I know this turtle makes zero sense whatsoever without any context, and I have to explain it later, but I'll flash and explain. A lot of zones, yes, but it is better to think of them in groups, and I know the colors are a bit close, but what did you really expect out of a system with 95 zones? Anyway, rather than explaining the system out of the box, I'll go through Nikolai's thought process written down on the blog post detailing the system. The Hersfeldt Bioclimate system has three goals in mind. The first one is minimizing proxies. Köppen uses a lot of proxies, so this system uses the most direct parameter available to delineate zones. The second is that definitions should be expanded to include unearth-like but still habitable cases. The third is that differences in biology should be accounted for to some degree, though there is the issue that we don't know about life there. On to the actual thought process now. The end state of any ecosystem without any environmental hindrances is a rainforest. Said hindrances on Earth include frost and low precipitation, but one could easily imagine a planet with areas too hot and too dark. Soil quality is not really significant anywhere and is a local thing, so the system does not cover that. As such, the system is first designed with Earth climates before continuing to more extreme conditions. 18 degrees is the tolerance limit for shallow marine coral, 10 for warm adapted tropical plants, 0 is freezing, -15 is the limit for frost tolerant broad-leaved evergreens, -20 is basically the minimum for even extremophile photosynthetic microbes, -40 is the limit for non-boreal plants, and -60 is the limit for needle-leaved evergreens. On Earth, the 0, -15, and -60 degree lines are most important for delineating forest types. As such, the first distinction is made between tropical, T, and C, cold, where T has a minimum temperature of 10 degrees. This forest type section operates on a model of plant profit. That means that producing sugar is a net gain and having to maintain leaves is a loss. And as a note on terminology, and I'm using the word evergrowth to mean any plant that keeps leaves year round and to make it color neutral, unlike the word evergreen. In group T, it is clement year round, so plants can just replace leaves at an arbitrary time where stochastic damage occurs. So it's dominated by broad-leaved evergrowths. In group C, the tolerance limits do something, but the more important distinction is in the growing season. At least initially, the growth interruption from winter is insignificant enough that tropical plants are mostly fine, as there's little interruption and growing new leaves is too expensive to be worth not wasting energy on maintain leaves that aren't photosynthesizing. Hence, this zone is also dominated by broad-leaved evergrowths. However, as winters get longer, the maintenance costs increase to the point where it's worth it to drop leaves and incur the cost of regrowing them, and the leaves can be optimized for the summer. This is the standard for most mid-latitude areas, so this area is dominated by deciduous trees. As the winters get even longer, though, plants can just wait it out generally while summer is getting even shorter. Thus, leaves are kept year-round, which results in needle evergreens. In the very coldest of these zones, it makes a final reversion to deciduous, but that is related to temperature tolerances. Hence, the C band is split into CT, subtropical, CD, temperate, and CE, boreal. Don't ask me why CD and CE are called that. Eventually, the growing season gets too short for even CE, so CF, tundra, and CG, no growing season, and CI, ice cap, are added. Now to address thermal tolerances. CXA zones, oceanic, are cool and don't need intense frost tolerance with a -10 degree threshold. CXB, continental, zones require a bit higher frost tolerance with a -40 degree threshold. And CXC, percontinental climates, need very strong frost tolerance with winters colder than -40 degrees. To trim zone, CT is always oceanic, turning into CDB if it's continental, and CXC is restricted to CE. CEC in particular corresponds to large forests in eastern Siberia. CG and CI are not subdivided further. Not so far, precipitation has not been addressed. That is dealt with now. Long droughts can be dealt in with two ways, either with the plant being deciduous and dropping leaves or making the leaves hardier, hence semi deciduous forests for short dry seasons. More dryness leaves dry forests that are all deciduous. Savannas with grasses between trees, and steppe where it is too dry for trees, and grasses or their equivalent on other planets dominate. Arid zones don't have a boreal analog, as dryness is a thing to be constantly maintained. Nikolai uses aridity to mark arid zones, which is the ratio of actual evapotranspiration to potential evapotranspiration. AET is given by any good GCM, and PET can be determined in detail with the Askey-Penman-Monteith method. The T band has those obvious aridity gradation, so the system starts there. Growth aridity is basically aridity with a weighted average towards the growing season, and has the short name GAR. In CT zone, some gradation is still possible, so CTF of a 0.75 AR and CTS otherwise that's not semi-arid, CA. All other zones just jump directly to semi-arid. Eventually, it gets too dry for forests, demarcating the A band. About 0.06 AR, widespread shrubs can still occur, so the band is split between AD and AH, semi-desert and hyper-arid desert respectively. CAA has cool winters and CAB has winters that are colder. AXA has cooler, warm winters and AXC has colder, frigid winters. Tundra takes precedence over semi-arid and cold barren takes precedence over arid. Now for Mediterranean and pluvial climates. Chaparral climates have the peculiarity that the precipitation is in winter, not summer as usual. They are delineated with the growth supply factor, basically the ratio of precipitation in the growing season to the whole year. Mediterranean climate patterns tend to obfuscate the growing season, so it is its own section. Pluvial zones are where soil runoff is significant and often correlate with temperate rainforests. Pluvial rainforests are here as they mark areas that risk turning into heathland. Not actual heathland marking though. To cut on zones, they aren't in Mediterranean, arid, tundra, barren, and ice zones. The zone codes that are pluvial just end in a P. This is the Earth Lake set done. Now to extend this. To start, T can be split between TU, which is clement year round, and TQ, where light is too low, like with warm poles, creating a similar analog to CD. TQ has all the same gradations as TU, except for rainforest. TF is where it gets too dark for large vegetation, and TG for any vegetation. Hot climates get their own section. High temperatures can cause plant damage, and even if not, photosynthesis is inhibited at high temperatures. It reaches a peak at 30 degrees and then starts declining rapidly. The zones are generally parallel to cold zones, with the exception that there is no boreal equivalent, as life can't just sit through heat. HXA is hot summers and gets above 50 degrees. HXB is torrid summers and gets above 70 degrees. And HXC is boiling summers and gets above boiling. HT cannot be torrid or boiling, and all other zones get all three thermal classifiers. Arid zones get an extra summer section. Don't XH. Don't ask me how non-Mediterranean hot climates are not the most common. They just aren't for some reason, despite warmer climate meaning more rain. Extraseasonal climates are where it gets both too hot and too cold. It's roughly analogous to hot zones. There are only two thermal classifiers: EXA with hot summers and cool winters, and EXB with either torrid summers or cold winters. Patterns carry over, and a new arid classifier, AXE, is added that requires both torrid summers and cold winters. That is all the land climates done. Now ocean climates. Ocean biomes are affected by a lot of things, but Nikolai only bothered with data directly available from Exoplasm. There is seasonal ice, OFD, and permanent ice, OFI. In ice-free waters, temperature is used. Temperate, OC, with temperatures dropping below 18 degrees but no ice. Tropical, OT, with temperatures staying between 18 and 40 degrees. Hot, OH, with temperatures above 40 degrees. Torrid, OR, with temperatures above 60 degrees. And OE, where it gets below 18 degrees and above 40, but not above 60. There are dark seasonal ice and dark zones too, OFG and OG respectively. That is the system done, and the video is over.